Hi guys, my name is Brian Irving Quiroz Ramirez. My teacher is Oscar Zarate San Pedro. This is the topic of thermodynamica, and my activity is 3 without the exposition with the unit 4. And estoy estudiando la ingeniería electromecánica en el TEC de San Martín Texmelucan. So the introduction is the second law of thermodynamics is a fundamental principle of physics that say energy always flows from hot to cold, and disorder entropy is an isolated system always increases over time. Think of a hot cup of coffee. It will naturally cool down to room temperature, but never the opposite. This simple principle explains why perfect efficiency is impossible in machines and why some processes in nature only go one way. This law is crucial for understanding how engines, refrigerators, and many natural processes work, showing us that energy transformations always involve some loss of the environment. The first topic is heat engines and refrigerators. A heat engine is a system that converts heat energy into mechanical work. It operates in the principle of the second law of thermodynamics, which dictates that some heat must always be rejected to a cooler reservoir, making perfect efficiency impossible. His function is heat engines take energy from a high temperature surge, perform work, moving piston like example, and expel unused heat to low temperature sink. The examples is internal combustion engines, steam turbines, and jet engines. The efficiency is determined by the ratio of work output to heat input. The theoretical maximum is given by Carnot efficiency, which depends on the temperature difference between the heat source and sink. The second topic is statements of second law of thermodynamics. The second law can be expressed through two case principles. Kevin Planck statement: it's impossible for any heat engine to operate with a single process and convert all the heat it absorbs into work. Some heat must always be rejected to a cooler reservoir. This sets the foundation for the efficiency limits of the thermal machines. And the Clausius statement: heat cannot spontaneously flow from a cooler body to a hotter one without external work being performed. This explains the natural direction of heat transfer. The third topic is the reversible and irreversible process. The reversible processes are idealized and occur with no entropic generation. They require infinite slowness and no deceptive effects, such as friction or heat transfer across the finite temperature gradient. And the irreversible process, by contrast, involve entropy generation due to factors like friction, rapid compression, expansion, or heat conduction. Real work systems are inherently irreversible, making them less efficient. So this is an example for reversible and irreversible process. The Carnot cycle is the fourth topic that says the Carnot cycle is a theoretical model that defines the maximum possible efficiency of a heat engine operating between two thermal reserves. One, isothermal expansion at high temperature, it's like heat absorption, and two, adiabatic expansion, there's no heat exchange, and third, that is isothermal compression at low temperature, heat rejection. For adiabatic compression, the efficiency of Carnot engine is determined by the temperature difference between the reservoirs. So this is the formula where Tc and Th are the absolute temperatures of the cold and the hot reservoirs. The entropy is a measure of disorder of randomness in a system. It reflects the degree to which energy is spread out and unavailable. For doing useful in thermodynamics, entropy helps to understand why certain processes are reversible and which energy transformation often involves some loss of usefulness. The key points about the entropy is 1. Direction of process. Entropy explains why heat flows from hot to cold and why natural process favor states of higher disorder. 2. Irreversibility. Real work processes always generate some entropy, meaning they cannot be reserved without external intervention. For instance, once ice met in water, it naturally doesn't revert without energy input. And third, that's equilibrium. Systems evolve toward to state maximum entropy, where they reach equilibrium and energy is uniformly distributed. The exergy is the portion of energy in a system that is available for doing use work. Unlike energy, which is conserved energy, is distributed during real process due to irreversibility like friction or heat transfer. The key point is usable energy. While energy itself is contained in the universe, exergy highlights how much of that energy can be converted into work in a given system. 2 is the environmental context. Exergy depends on the between a system state and surroundings. For example, a hot object has energy when placed in a cooled environment, as it transfers heat to do work. And the applications are efficiency. The exergy analysis identifies inefficiencies in engines, power plants, and another energy systems. And the sustainability, it helps measure the effectiveness of natural resources and their environmental impact. The reversible work and exergy balances are the maximum work output achievable in the idealized process without entropy generation. The exergy balances in closed system will be. Can you show you more in this point? In open system, our control volume involves interaction with their surrounding through the exchanges mass, heat, and work. Exergy analysis in so much system evaluates the quality and usability of energy flowing in out. Key aspects include exergy associated with mass flow. Mass entering or leaving the system carries exergy related to its physical, temperature and pressure, chemical, kinetic, and potential properties. The energy efficiency, exergy destruction areas from irreversibilities such as friction mixing and heat transfer across large temperature differences. Minimizing these irreversibilities can exchange system performance. The applications. Common applications include turbines, compressors, and heat exchangers. Analyzing the energy transfer helps in optimizing process and minimizing energy losses. In closed system, there is no mass transfer across the system boundary, but heat and work interaction occur. Exergy analysis in these systems assess how efficiently exergy converts into work considering irreversibilities and losses. The exergy quality, the total energy in a closed system includes the internal energy, potential energy, kinetic energy, and environmental reference state exergy. Destruction quantifies the inefficiency in converting energy into useful work. The optimization potential reducing exergy destruction so much as through better in solution it or optimized process design leads to exchange energy efficiency. This principle is fundamental in design systems like thermal storage or closed cycle power systems. So the conclusion is thermodynamics provides the foundation for understanding energy conversion efficiency and limitations in energy systems. The second law highlights the inevitability of energy losses due to entropy and the direction of process, while the Carnot cycle reserves as a theoretical benchmark for efficiency. Entropy explains energy dispersions, while energy quantifies usable energy and identifies inefficiencies caused by irreversibilities. Open systems focus on energy and mass transfers, crucial for turbines and compressors, whereas closed systems analyze heat and work interaction for optimization. Together, these principles get to design of efficient sustainable systems, balancing energy and minimizing waste, essential for a modern energy and environmental goals. So this is my exposition for the competencia 4, actividad 3. Muchas gracias.